Okay, hi everyone, welcome back. My name is Alexander Kreu. I'm one of the co-organizers and I'm the one closing this day. So we are lucky that the AFLOW team, or part of them anyways, agreed to come back today to answer your questions that you might have after the hands-on session on Tuesday. So please ask your questions in the chat, or you can also unmute yourself. And I think Cormac, I've seen Cormac there, and David and Enrico, and did I miss anyone? Well, anyway, so there.
Yeah, I'm here too.
So am I.
I think we're all here actually.
Perfect.
So we can field plenty of questions.
You can ask your questions yourself, you know, like Cormac to David and Enrico to. Okay, yeah. So just don't be shy. Ask your question in the chat or just directly. If you like. I mean, there's still about 40 people around. Okay, so there's the first question by Manuel. Is there a routine to run automated nudged elastic band calculations? I guess within AFLOW, right?
I think there is, well, there was something attempted a long time ago. I'm not sure if it's how well it works. I've never tried using it. I don't know if anybody has tried using it recently in our group. There was some stuff that was done. If you look in the manual, there's something mentioned about it, but I'm not sure how functional it still is, if it's still there. And it's not something we've used recently, and it's not. So I can't say how reliable it is. Or I know we had some. All I know is that there was some mention in the manual, and then there was also some, like when I talked to people, they said it didn't really work very well. So, but it's not something we've tried recently.
There's another question by Jordan. Just before I come to that, so Cormac, maybe in general to extend this question. So if you have something that you want to do yourself, like let's say a nudged elastic band or something more exotic, how hard is that to, you know, to use with AFLOW or to integrate into AFLOW? Or I mean, how would you approach this? Or does one have to approach you, or how should one do that?
So if you want to do something, that it's probably best to approach us, and then we'll sort of to work together as part of a collaboration. Especially if something needs to be implemented within AFLOW to do this. Yeah, because this can be quite a large. So sometimes it might be something that's a small tweak. It's very straightforward to do. Sometimes it might be something that's like a major project.
Okay.
But yeah, if you send us an email, we'll send you know if this is possible or not, or how much work. We can try and think about how much work it would actually be.
Okay, cool. Okay,
so then I think the next question is about prototypes. So maybe if David.
I'm not familiar with the nudge elastic band calculation. Are these this is something I imagine you can run with VASP. I will say that it is possible to run AFLOW with additional settings. Let's say if the nudge elastic band calculation requires you to change some settings in the in-car, you can actually explicitly set what you want the in-car to look like through AFLOW. So you can still run automatically leveraging all of the error corrections with VASP and all that, but using AFLOW as a wrapper for VASP. So I'm not really sure about the approach. I'm not very familiar with it, but there are ways of changing what the settings are in the in-car that we can discuss if you're interested.
Maybe I can say something about that. The nudge elastic band calculations, they have often problems with convergence. And the way that VASP error handles the errors is quite so I can imagine it's quite difficult to automate that, at least from my perspective, but I don't have any experience with these stuff. So that's why it might be difficult, but I don't know.
Yeah, I mean, the error correction that's in AFLOW is probably the most complex part of the code. And it's like even like standard error correction, and that's just for VASP. Like if you go to other codes, like at least with VASP, the error correction format is relatively standardized. With other codes, it's very difficult. It's not an easy thing to do. That I can tell you. That it's probably like the sort of, it really is like really part of the core of what AFLOW does. And it's not, so extending it is something that's a lot of work. Okay, so David, do you want to talk maybe about the history of the prototypes?
Yeah, I can. So yeah, for the prototype question, somebody asked how were prototypes identified for the prototype encyclopedia as opposed to structures that aren't considered a prototype. So we've been building upon the prototype encyclopedia. So I think I mentioned in the talk that in part one originally was started by Professor Manuel when he was at the Naval Research Laboratory. And so these were mostly experimentally observed structures or common structure types like rock salt, corundum, things like that. And then for part two, we were extending it to the different space groups. So we were trying to have at least one representative structure in each of the 230 space groups. And then we're working on part three right now. And so this, we've been trying to go through the literature to find the strukturisch designations and to have a complete set of those. So that's kind of how we've been building upon the encyclopedia. And for future versions, we've actually developed a tool called AFLOW Extel Finder, which is to identify unique crystalline prototypes. We didn't get a chance to discuss it in our sessions, but this is a tool that can help us to automatically find prototype structures. And we've already had that lined up for parts 4 and 5 to give us new structure types. So hopefully that answers your question. And so that's where we're at right now with the 590.
Thanks.
Yep.
Are there any other questions? Just shoot right away. Now it's still for free. There's a follow-up. Yeah.
Oh yeah, so I guess for the follow-up, yeah, so originally it was more by hand, so finding the experimental structures, and now now that we have the baselines that we want to have a more comprehensive set, so now we're using this automatically. So we're using this automatic approach. But yeah, no problem.
So, anyone else?
Okay, so I think maybe while we're waiting, I think there was one question at the last session, maybe a bit about the, that's called pseudo-binary phase diagrams. So this is like something where if you want to go from a, let's say you have zinc sulfide to zinc selenide or something like this. So maybe, I don't know if Corey, if you want to talk a little bit about the partial occupation code. So this is something that's not quite an AFLOW yet, but we have a lot of the pieces. Corey, I think
yeah, so no, I'm here. Sorry, 1 second. I don't see the question. Where's the question?
No, this is a question that was asked the last time. Remember the question we had the last time about the pseudo-binary?
Absolutely. So, well, okay. So the pseudo-binary. Well, so to address the pseudo-binaries, I recommend that okay. So there's the partial occupation module through AFLOW. Okay. So you know, Professor Cutarello, one of the major highlights of his talk was addressing disorder. This system is disordered because you're going to have sites in the crystal that are not uniquely occupied. That is to say that there are some sites that may be partially occupied with, let's say, occupant A and occupant B, whether it's sulfide, selenide, or what other occupants you have. So we have a particular approach for how to model such systems, and that includes taking this disordered system, which cannot be represented by, say, one configuration or an ordered representation of a crystal like you would with VASP, and decomposing it and representing it as a series or an ensemble of ordered structures. Okay, and so a system like the pseudo-binary that you presented instead of representing it as one VASP calculation, we might have it be represented by statistics of an ensemble set. And so this is something that AFLOW can do for you automatically. I would be happy to I think we put last time some of the previous workshops we've done on the session. I can put that again in the link here. But basically you basically put in what we have, what's called a part car, which is a generalization of a post car, which is in VASP. And this allows you to specify sites that are not just that are partially occupied by a certain percentage, 0.25, 0.75. You can even have occupancies inside. And with that part car representation that AFLOW understands, it can automatically generate the ordered structures for you. You run these with VASP, and then AFLOW can also perform the statistical analysis to get the trends and the properties for the overall structure, which is going to basically be a Boltzmann average of the ordered structures. So I'm gonna actually put. I mean, I would be happy to we can do another session on POC, but I'm gonna plug into the chat 1 second. I'm going to plug in a previous workshop that we held, a recording of it, so you can see some of the options. What are the settings for it? This module is how we were able to do these analysis that Professor Cruderlo was talking about for the disordered systems. So let me go ahead and plug that in for you. Here you go. So if you go to this link, we actually have the recordings for a lot of the past workshops that we've done. And among them, you'll find, I'm going to give you the specific section to look for disordered systems. If you want to look for, right here, if you want to go under this section, you'll find a previous recording of the workshop. And there's also the relevant slides. So with the slides, you can actually copy and paste the commands directly into your command line once you've downloaded AFLOW. And you can run the POC algorithm for any system that you're interested in. But yeah, so that's a little bit about the system. From a user perspective, I think it's important to know that a lot of these processes are automated in AFLOW, so you don't need to know all of the details about how we create the ensemble set, the representative ordered structures. All of that is more or less taken care of you for AFLOW. And of course, if you're additionally interested, the references of how we go about doing that process are presented in the paper that's in the slides.
So I think there's a follow-up question there from Gordon Peterson for you, Corey, about the commensurate versus incommensurate.
There's the same procedure applied to commensurate and incommensurately modulated structures as well. What do you mean by commensurately and incommensurately modulated?
Are you talking about misfit layer compounds or something like that?
I think, Gordon, you are muted. Or at least we cannot hear you. No, still not.
My guess is that he means that let's say like one endpoint is a wort-side phase and the other endpoint is a zinc blend phase of the
yeah, so
I see.
From what I understand about the commensurate and incommensurately modulated structures that I know, like misfit layer compounds, I don't think that POC does that because they're more structurally disordered, not chemically disordered. So misfit layer compounds are two different structure types that are layered on top of each other, and sometimes they're commensurate and sometimes they're incommensurate, so the structures don't align.
Right.
And it's not like chemical disorder like we have in a traditional solid solution. So that's not necessarily something that POC can do.
As to intermetallics, we can often see crystal structures that cannot be described with the 3D units, but are also periodic. I see. So I think it looks like Marco, you may have been you were right. I think what you're referring to is structural disorder, not necessarily chemical. So there are to be clear, there are many types of disorder that can be present in a particular material. The disorder that I'm talking about is chemical disorder. So if you're interested in representing a chemically disordered system, you would use the POC module. But for something such as structural disorder, that's not something you would do with the POC module. I mean, obviously there's other ways of representing that. And we do have some experience in the past with representing, for instance, bulk metallic glasses and the like. Maybe Cormac and David can talk a little bit more about that. So when doing a vast calculation, you need to approximate with some kind of periodic cell as you would a unit cell containing mix. Exactly. So you would know, for instance, the lattice that you're working with. So Professor Kudero talked about yesterday these disordered system carbides, these disordered carbides. We know that they exist on an FCC lattice. And they're starting off from, the base structure would be like a binary rock salt structure. So we know what the baseline parent structure is. With that information, we can go ahead and partially occupy the sites within it with more occupants. And we build a representation for that structure and the corresponding derivative structures for it.
Whereas with misfit layer compounds, for example, you don't have that one 3D parent structure. You have two different structures or some kind of a weird structure that you need to describe in other means. The POC approach requires a parent structure that has one symmetry, if that makes sense.
Absolutely. No problem.
Nusaiba just asked sort of privately about the recording of this hands-on session, and just to remind you all that we put the link in Zulip under the respective session of Tuesday. So there you can also watch it again, and I guess approach the AFLOW team, through the usual channels that you can probably find on the website of AFLOW.
Once we have the chance to edit the video and kind of piece it into the different sessions, we will upload it to the link that Corey posted.
Okay, any other questions? At the moment, I don't see any other questions. Anyone? I mean, we will certainly link also the workshop. I mean, your workshop in this site on Zulip. So if anyone wants to come back to that, they can do so. All right. I think, I mean, if there are no more questions, then I think we should thank the team again, Cormac, David, Rico, Corey. Just, last question. So how long did it take to build the database?
Oh, I think it's, so like this, well, depends on what you mean by the database, but certainly the data that's there has been built up over probably the best part of 20 years. There's some calculation in the database that might go back as far as 20 years. Most of the data is actually relatively, like when I first joined the group, there was maybe I think we had about 300,000 entries. Now we have about 3 million. So the rate of increase is also increasing, if you know what I mean. But yes, but there is data that goes back a long time. And that's partly, so I think one of our strengths is that because we have accumulated the data, then, like, for example, Corey mentioned earlier about the metallic classes. That was something that was built up on, it was basically, like, there was no really additional DFT calculations done, like, for that paper. We just used existing data, something that, you know, we might have data that was calculated 5 years earlier that was basically being reused in this new model. In terms of the current structure form of the database, well, maybe I'll mention a little bit about how the database is organized underneath, because this is something that we didn't really get to address. So our actual underneath lying database is actually really just stored in a, let's say, call it a human navigable directory system. And then the actual, like, the SQL and all this is actually just a layer on top of this. And this is quite nice because it's quite robust. It's quite future-proofed that, you know, if we want to move to something other than SQL in the future, we don't have to throw out all the data. The data is still there, but it's very easy just to build a layer on top. So this layer on top is a bit more recent. It's probably in the last 5 years it's really developed.
And then what about the computational resources? I guess this has increased exponentially over these 20 years, right? I mean, the resource that you used.
The resources you used to calculate? Oh, sorry, go ahead, Cormac.
Yeah, well, maybe if you want to address it. So we use we have our own database. We also use cluster. We also use databases from collaborators. So it's sort of developed over time. So our own cluster is actually pretty decent. But we also use then, you know, we have collaborators that also have cluster or access to clusters that we can use and so on. So then next, there's another question about, can the database be downloaded or installed and used offline?
No, it cannot be. We're talking about hundreds of terabytes of data. I don't even think you could store it if you wanted. And so the database itself, you would need an internet connection to store it. I mean, this is a problem we're always facing, is constantly having to buy new disks and new ways of storing things. So that problem is a very challenging problem. Obviously, I don't think you're very interested in it. I wouldn't expect any of our users to be interested in it, but it's something we're constantly having to innovate. And so we have to, in the background, manage the space and the hardware and all this stuff. And we make sure that the interfaces for the users can still access all of the data, even if it's across multiple hard disks or whatever it is. So it would not be something that's accessible online. You definitely need an internet connection to connect with our interface for our setup.
Yeah, that would certainly be the case for the actual original VASP DFT calculations. I mean, in principle, there's a REST API, and you can download, let's say, the processed data. And that in principle you could do. I mean, we wouldn't necessarily advise you to do it because the database is continuously being updated. More materials are being added. And I would say certainly if you want to just interface with the database, I would use the AFLOW search API is the best way to do it. Do you have a platform? So then there's another question about a platform where any experimentalists can upload their data. This we don't do. We like, one of the focuses for our database is to make sure that the database is, the data is, let's call it, like, we put a lot of emphasis on consistency of data. So therefore we don't really host any other people's data. We only really host our own data. They're like, okay, if you have computational data, you know, there are other locations where you can upload your data, like for example, the Nomad platform, or I think the Materials Cloud that Professor Mazzari was showing in the last session. For experimentalists, I don't know if there are such, I'm not really too familiar with it. I know that there's a lot of work being done, but the experimental data is far more fragmentary. It's not as easy to access automatically because there's, like, a lot of the time machines have their own proprietary formats and so on.
Oh, absolutely. Definitely available for collaborations.
I know that NIST are doing a lot of work on materials data, experimental materials data curation, but I'm not sure if there's anything available yet for experimental data that you can upload. That I'm not familiar. I mean, it would be really nice for us because we would really love to have a source of experimental data that we could then use to, like, for let's say, for doing validation of our models and these kind of things. But it's very fragmented at the moment. But we would really love if there was a centralized experimental data platform that we could pull data from to do like our own model training and validation, but that's not.
And maybe you can, just to interrupt, you can keep that question in mind and ask this again tomorrow, because tomorrow we will have Professor Hong Wang speaking, and he is an experimentalist, and he will speak about this sort of from the experimental point of view, and also, you know, what to do with the high throughput measurements and how to store that and so on. So I think maybe you can just ask this question tomorrow again, and then, you know, there will be some answer, some direction. Yeah, sorry, I just didn't want to interrupt.
That's great. I want to just add on to what Cormac said. So it is I mean, the post-processing data, yes, you can download it, but I think he made a very important point when he said that you wouldn't necessarily want to do this. A lot of the post-processing that AFLOW does, this data is constantly changing, and so we put in a great effort to make sure that the post-processing that's done by AFLOW is something that can be done on the fly from your laptop, right? Assuming you have an internet connection, because this data is constantly changing. So the best example I have is the convex hull. You know, the data can be stored in the database, but this data would become obsolete more or less on a daily basis, because we're constantly adding more data to our database. We're running in different computers, and so this data would become obsolete every day, more or less. And so you don't want to store these things. Some of these properties are better if they're done on the fly at the moment that you're interested in the data. So it's a different paradigm of thinking. It's not some of the data certainly can be stored if it takes a long time to calculate these DFT calculations, but some of this post-processed data, it's something that does change day to day depending on whether you have new data.
So an example of such a quantity that could change would be, for a particular entry, would be its distance to the convex hull. Because if you add another entry that's lower down, the convex hull shape changes, and therefore the distance to the hull will change. And this is actually, you know, it's probably the most important factor when it comes to looking at thermodynamic stability. And, you know, it's something that in principle is not a fixed, it's something that's sort of something we're always trying to improve.
But I guess that exactly this kind of approach, right, would be very compatible with the experimental way of working, right? Because they probably also have constantly an inflow of new results, and then they have to adjust things that can be calculated from this data that they measure, right? So this is probably quite nice. Okay, any other questions from the participants?
Hello, please. Hello.
Yeah.
Thank you for your answer. Please, I would like to ask, since you said the data keeps changing on a regular basis, does that, what about even citing such information? Is there not going to be a conflict if I cite?
If you want to cite, well, generally speaking, if you are trying to cite particular, okay, so there's a couple of things. So if there's a particular entry in our database, this will have what's called an AUID, so an AFLOW unique identifier. So this will be fixed and unchanging, and this is a property of a particular calculation. So while the data from a particular calculation won't necessarily change, so for particular, one particular material, the thing is that the for distance to the something like a distance to the convex hull is not necessarily a property of one material; it's a property of the entire material system. So so that's what will change. So if you cite, then there'll be something like, there'll be a combination of versioning, dates. So if there's a paper on the REST API, which will include some information about how this is generated. And let's see if I can, give me a couple of minutes and I'll pull up the, I'll post the link to this paper in the address. And then, but in terms of actual just general citation, from our point of view, what's probably important to cite is more the methods that so the papers describing the methods that we use to generate the data is more what we tend to publish in terms of actual publications. But if you give a versioning, a date, then this will help with reproducibility of a particular entry.
Yeah. Okay, thank you so much.
Hello, can you hear me? I have a question about the database. Do you have any like redundant copy in the background of your database, or is just one copy?
No, we have the database is backed up with several redundancies. So we're very careful about making sure that there's redundancies in case of failures. You know, there's hard disk failures. You know, we do have a whole system of that. And yeah, so I would say again, I mean, it's a good question, but no, I wouldn't worry about data disappearing overnight one day. I mean, we have plenty of redundancies of the data available. So I wouldn't worry about that from a user perspective, but it's a good question.
Actually, I have another question. Is we see a lot of like inorganic database, AFLOW or others. We hear like material discovery. And is there any like crossover, like the same data, same compound between these databases?
There are. I would say that one of the features is, I mean, there are going to be certainly there's going to be databases that have the same, you know, for instance, we pull from some common databases, maybe from the inorganic crystal database, for instance, and so there might be some other databases that do the same and process them with DFT, let's say. So there is crossover, but one thing I would say is that, you know, one of the focuses we have are on inorganic intermetallics, right? And so we really focus on that subsection of crystallographic data. We're branching into disorder. There are others that sort of focus maybe on materials that would be used for, let's say, batteries or things like that. So everyone sort of has their own particular focus. And in that respect, they branch off with different modules, different approximations, and they create their own ensemble of set of materials in that direction.
Okay, thank you.
Absolutely.
Maybe there may be some last question for today. Then just make yourself noted, because otherwise I would think we thank the AFLOW team again. I was trying this a couple of minutes already ago. Thanks for coming back and for answering the questions. I think it's good because you know, everyone needs some time to think over, and then you don't have the right question at the moment when the presentation is going on. So thank you guys. Then I would like to thank all of the speakers. I mean, the lecturers are not here anymore, but I thank the speakers of the contributed talks, which were very interesting. I have 3 things I just want to mention. The first thing is that we have the poster award survey online. We sent a link to the chat a couple of minutes ago, and it's also on Zulip. So please vote for your favorite poster. Actually, Cormac, David, Rico, and Corey, I think since you're on Zulip, you actually can also participate if you like. But then you have to look at the 60 or so posters. But you only have to select 3. So anyways, you can take the first 3 or something like that. I don't know. Then the next thing is that we have also like a Google Earth, how to say, flyover the campus. And that's also linked in Zulip. So if you're interested in how it looks like in Dresden, or looked like in Dresden a couple of weeks ago, then you can use that link and play around and fly over this building we are sitting in now, and so on. So that's also linked. And last but not least, so tomorrow we start at 2 local time with the lecture of Professor Hong Wang. And then we will sort of wrap up with a small roundtable kind of discussion after a short break. So thanks again, everyone. Have a nice day. Have a nice evening. Good night. Good morning.
Thank you, too. Thank you. Bye-bye.
See you soon. Ciao.
Ciao, thank you.
Thank you.
Thank you.